Okay, we're 1 minute late, but should work. So our last talk of the day is Artem's Chernikov's third lecture on model theory combinatorics. Yeah, you can speak Artem, and thank you again.
All right. Yeah, thank you. So today I would like to talk about distality and some of its combinatorial consequences. So distality was introduced by Pierre Simon as an attempt to isolate somehow purely unstable behavior in within NIP series. So let me, the original definition is like this. Let T be an IP. So T is a complete theory as usual, yeah. T is
some problem with the audio.
There's a problem with the audio?
Like you hear it slightly more poorly than the previous days. I'm not sure. Did anything change in your settings? Otherwise, it should be okay.
But you can hear me now?
Yeah, it's just, I don't know, it sounds worse.
Okay. I don't think I've changed anything, but
no worries, I think that's better.
Okay, let me just continue. So is distal if every infinite indiscernible sequence so if for every infinite indiscernible sequence indiscernible sequence, let's denote it as let's say I, and let's say it's of the form AI. So I in I1 plus I2 plus I3. So we have three infinite linear orders without endpoints. Okay, so given an infinite indiscernible sequence indexed by linear order like this, if we have that for some, so for any, excuse me, for any A1, A2, we have that if, when I put A1 in the indiscernible sequence first, so I have AI, I and I1, concatenation with this one element A1, and then continued by I2 and I3, so AI, I and I2, and I3, okay, is indiscernible. And similarly, if we add A2 in the second cut, so we have, maybe I shouldn't call them A1 and A2 because, well, never mind. Or we have I and I1 plus I2. And by plus, I just mean the linear order given by the taken first, let's say I1 and then I2 consecutively. Yeah? Concatenated with A2 and concatenated with the rest of the sequence, so AI, I and I3. So if both are indiscernible separately, then it already implies that putting both elements into the sequence is also indiscernible. Okay, so then AI, I and I1 concatenated with A1, concatenated with AI, I and I2, concatenated with A2, concatenated with AI, I and I3 is indiscernible. And I just remind that indiscernible means simply that any formula in any number of variables simultaneously satisfied or not satisfied by all increasing tuples from the sequence. Yeah. So I have to draw it. We have these three pieces of the sequence, and then either I can put A1 here, and this is indiscernible, or I can remove A1 and then put A2 here, and this is indiscernible. Yeah. If we have the separate indiscernibility conditions, then already the whole sequence with both points put in the corresponding cuts is already indiscernible. So this is a model theoretic definition. And exercises to see, for example, that this cannot happen if our indiscernible sequence happens to be totally indiscernible, which is always the case in a stable theory. So it's easy to see from this property that any stable theory is not going to be Distal. Yeah. So this is the original definition in terms of indiscernible sequences. And for combinatorial applications, what we proved is a more convenient property. So I'm going to change the slide unless there are any questions about this definition. And this is something we proved with Pierre. So equivalently, we say that a formula in two variables, phi of x, y, well, in two groups of variables, x and y, is Distal if there exists a different formula. If there is a formula psi of xz, so note here that x is the same variable as in the original formula, but z is possibly a different variable. Yeah. So there is a formula psi of xz such that for any finite set A, a subset of the y sort of our model, we can write the whole model as a disjoint, well, not even necessarily disjoint, just as a union. So we can write so we can decompose the x sort of the model as a union of some instances of this formula psi. So we can write it as the union psi of xbi for I less than n, okay? Such that for any I less or equal than n, and any two elements or tuples AA prime, which both belong to a single, to one of these cells. So for example, they belong to psi of MBI. Then we have that they have the same phi type. So the phi type of A over our finite set A is equal to the phi type of A prime over our finite set capital A. Okay, so this can be viewed as a very weak combinatorial trace of a cell decomposition. Like, let's say, cell decomposition that one has in or minimal theories, or let's say periodic cell decomposition. So maybe if I try to draw something, what I'm saying here is the following. So we have, let's say this is our sort mx, yeah, and this is my, and so assume we fix some finitely many parameters in my. This is our set capital A, and note that psi, this formula psi here, it depends only on phi. So it doesn't depend on the choice of A. Of course, if since A is finite, for each finite set separately, it's easy to choose a formula psi with this property, right? We can just pick formulas given by the complete phi types. So we can take big Boolean combinations of instances of phi. So what's important here is this uniformity, that the same formula psi works for all for arbitrary large finite sets simultaneously. Yeah. Okay. And so what I'm saying is that given a finite set of parameters A, we can cut the whole model, and note that the cells can, in principle, intersect. So let's call each of these a cell, or a cell in a distal cell decomposition. Yeah. And so we have the cells, and now if I take 2 points inside the same cell, they have the same type, phi type over A. Yeah. So they're connected to exactly the same elements of A by the formula phi, if you think about it as a bipartite graph. Okay. So this is what we can call a distal cell decomposition, or a variant of it. So let's call this distal cell decomposition. Okay. And so what we proved actually is that T is distal in the sense of the previous, in the sense of the original definition I just gave on the previous slide, if and only if every formula phi admits a distal cell decomposition. Let's say psi, yeah, like every phi of xy. Here we have psi of xz. Moreover, even though it is not necessary to require it, but then here we could have required that the BIs are actually tuples from the same finite set A. So not necessarily elements of A, I'm abusing the notation slightly here, but let's say tuples. Let me write it like this. Let them A to the omega. So the parameters can also always be chosen from within this set. And sometimes this is called strong honest definitions in an IP theories, in distal theories, excuse me. Sometimes it's called distal cell decomposition, yeah, depending on what you're trying to do with it. All right, so this is equivalent. It's a combinatorial argument. I mean, combinatorial model theoretic argument. I'm not going to prove the equivalence, but we will see that this one is actually more, so this version of the definition is more useful for various combinatorial applications, as you can maybe imagine, right? Because here we have something like formula by formula property again. Yeah. Okay, so this is the important property of distal theory that we want to work with. Now, to mention some examples of distal theories. So I already, I guess, alluded that this property, distal cell decomposition, can be viewed as a trace of some stronger cell decompositions with geometric properties. So for example, in minimal theories, or even weakly or minimal, P minimal, like QP, for example, or let's say the valued differential field of trans series, if that's your cup of tea. So all of these are examples of distal theories. Yeah. And the easiest way to see it is probably indeed to use an appropriate cell decomposition or appropriate result for the corresponding theory, and try to verify distal cell decomposition as on the previous slide. Moreover, when you are trying to prove something like this, let me just remark that it's enough to check that every formula phi of xy with x a singleton has a distal cell decomposition. So as it tends to happen with various model theoretic properties, we can combinatorial model theoretic properties. In order to verify it, we can reduce to checking it for just for formulas in a single free variable. Okay, so these are some examples. In particular, distality covers the semi-algebraic context, right? So of course we have the field of reals here. Well, less than, I guess. Yeah, and so because there's quite a big body of semi-algebraic combinatorics. So distality seems to provide a correct more general context for all of these kind of results. All right. So now let's go back to our discussion of regularity, of semi-ready regularity. And so in the context of distal theories, we again have a strengthening in an orthogonal direction to the stable case. So let me state it like this: theorem. It was proved by me and Sergei Starchenko, generalizing the semi-algebraic case that was already known. So the situation is basically the same as always, well, as in our previous discussion. So we assume that we have two commuting Kistler measures, mu of x, mu of y. So let this be pairwise commuting. Definable Kistler measures. Kistler measures, excuse me. And assume we have a relation, a definable relation. So let E of xy be definable. And distal. Okay. So distal in the sense I have just defined, in the sense that it admits a distal cell decomposition. Yeah. And here, moreover, we have to assume that the whole theory is an IP. So in fact, actually, it's not needed. Sorry, I'm only going to present a proof today which uses that T is an IP, but for the result itself, it's not needed. So let me state it in full generality instead. Okay. So assume we have a definable distal relation like this. Now, for any positive real number epsilon, as usual, our allowed error term, there exists so there exist rectangular formulas. Well, let me write it, I guess. There exists, let's say, AI di. So AI of x, di of y, definable. And now let me also state that there exists AI prime of x, di prime of x, definable. Finitely many, so for I less than some n, let's say. Okay. Such that we have the following. So we have that the disjoint union of the product of AI of x. So product I can guess for formulas I can just write it as a conjunction. AI of x, di of y, for I less than n. So this is contained, it's an actual subset, yeah, of R, not R, excuse me, of E, and this is contained in the disjoint union of AI prime of x conjunction with bi prime of y for I less than n, yeah. So we can sandwich the binary relation between these two. And moreover, the measure of the difference of these two sets is very small. So we have, okay, let me call this, for example, E1, and let me call this whole set E2, okay? So then we have that the measure, so mu tensor nu, because these are sets in two variables, of E2 minus E1 is smaller than epsilon. Okay, so you see, So given a binary definable set, we can find a bunch of rectangles. Yeah, not just approximate inclusion, actual inclusion, so that the up to arbitrary small error. So in particular, in terms of the semi-radius regularity lemma, what it tells us is that, so let me write it in particular. This means that in semi-radius regularity lemma, on every good pair, so every good pair not only has density close to 1 or 0, yeah, not only that the edge relation E has density close to 1 or 0, but that it is actually homogeneous. So every good pair is homogeneous in the sense that it actually has all the possible edges, or it has no edges at all. Yeah. So not only it has like almost all edges or almost no edges, but actually it is homogeneous in a precise sense. So it has literally all edges or no edges at all, except for a small set of bad pairs. Right. So if you remember what for stability, what we proved is that there are no bad pairs. So here there are going to be bad pairs potentially, but on every good pair we have a stronger condition that not only density is 0, 1, but in fact they're homogeneous. Okay, so this is the statement. So I want to sketch a proof for it now. So if this is okay, I'm going to go to the next slide unless there are any questions. Okay. So yeah, sorry, go ahead.
No, we're good. We're saying.
Ah, okay. So, all right. So let's prove this. And I guess I'm going to assume an IP. So of the whole theory. Yeah? So assuming that the whole theory T is an IP. As I have remarked already, this is not necessary, but it makes the proof considerably more complicated. You will see where it is used, yeah. So, okay, so assume we're given this this edge relation, yeah. So let E of xy be as in the statement of the theorem. Okay. Somewhat similarly to the proof of the NIP case, we can consider the following formula. So let's say xi, so I'm going to write xi of y, z, x1. So we have two groups of variables here. Y is the first group, yeah, and then we have z, x1, which we take to be the following formula. For all x, psi of xz implies E of xy, symmetric difference with E of x1 y. Okay, and let us denote this first part by the first part by this, I mean this part. Let's denote it by theta of yz. Okay, note that there's variable x doesn't participate here; it's quantified. Yeah, and here psi here by yeah. So psi is chosen to be the distal cell decomposition for E. For the formula E of xy. All right, so we have this formula. So first of all, note that we have trivially that theta of yd and psi of yd together imply r of xy. This is literally from the from this formula, yeah. So trivially, by the way we chose the formula. Now we want to use that this whole formula C is an IP. So by assumption,
sorry,
C is an IP. Yes, question. Yes.
yeah, what is R?
What is? Oh, I'm making no sense. This is E. I'm sorry. This is E. Yeah. Is it okay?
Yeah.
Okay. Okay. Thank you. Yes. So right. So by assumption, the formula psi is an IP, because we're assuming that the whole theory is an IP, right? So in particular, this formula with the corresponding partition of the variables, so y and zx1. So now we can use the VC theorem, just like we did in the IP case. We can use the VC theorem for this formula, right? So by the VC theorem, some elements, so let's say B1 through Bn, yeah, some elements, such that the average of these points approximates psi. Yeah, so such that we have that this average measure, so 1 over n, let's say, of y is equal to b1, I less than n. So this this measure approximates the measure approximates, I mean, up to epsilon, let's say. So we have this fixed epsilon, remember. Approximates the measure of every instance of psi. Right? So this is using that psi is an IP. Without this assumption, this step would, well, I'll finish in a second, but this step would get much more complicated. It is possible to do, but somehow you need to use some random sampling techniques and things like this. But for our purpose, I guess I should have remarked that every distal theory is an IP. Yeah. So every distal formula is in particular an IP. So the problem is that even if you start with a distal formula, which is an IP, the formula psi, which gives the distal cell decomposition, is not necessarily an IP, unless you assume it somehow globally. Yeah. So that's why this global assumption is being used here. Okay. So we have this, right? We have this so we pick these points, which give an approximation up to epsilon, right? Okay. So by distality now, well, by the choice of psi, which is a distal cell decomposition, so we know that we can cover my x mx, excuse me, I should have said, I guess, mx as a finite union of instances of psi, right? So for example, let's denote it like mx, I keep writing y for some reason, mx is covered by the cells psi of x di, let's say, for I less than some m. Okay. So so what this means is that we have the following condition for any two elements, let's say a prime, which both satisfy psi of x di, right? What we have is that the type, the E type of A over B1 through Bm is the same as the E type of A prime over the same finite set, B1 through Bn. And this is N, excuse me, not N. Yeah, we have our elements B1 through Bn, and we choose a distal cell decomposition for this. Yeah. Okay. So we have this. Now, finally, we can take the following set. We take the union. Whoops. I don't know why I wrote it disjointly. So we take the union of theta of y di and psi of x di. Okay, so we take this union over all I less than n. So note that this is a rectangular, a union of rectangles, right? So if I go back for a second, this is going to be this set. Yeah, so this is going to be my E1. It's a union of rectangles, right? Because thetas only speak about y, and psi's only speak about x. Okay, and note that this is actually a subset. Well, subset implies here, I guess I'm confusing sets and formulas. So formulas and sets that they define. So this implies this is contained in E of xy. So this you can see from the definition if you think about it for a second. So what remains is to show that it is big enough. Yeah, we need to show that it has almost full measure inside E up to epsilon. So let's check it. So take any A realizing psi of x di. Okay, take a realization like this. Then we have that theta of y di intersected with this finite set B1 through Bn, okay, is equal to E of A y intersected with B1 through Bn. Let me write it clearly. So intersected with the same set, B1 through Bn. Right, so the intersections coincide. But remember how we chose the BIs? We chose them to approximate the measure, right, of the instances. So it means that if such two appropriate instances agree on all elements of BI, then they must have almost the same measure. So hence we have that the measure mu, no, it's on y, right? So nu, excuse me, the new measure of the symmetric difference of theta of y di, symmetric difference with R A y, yeah, is going to be small. It's going to be smaller than epsilon. Okay, so this happens for every realization A, realization of psi. So if I pick any realization of psi, let's say A, we get that the measure of the corresponding fiber is small, right? But now remember how the tensor product is defined. It's defined by integrating over the fibers, right? So this then by Fubini. So if each fiber is small, if for any fixed A, the measure of the symmetric difference of the fiber is less than epsilon, then when I integrate over all fibers, I'm still going to get the measure smaller than epsilon. So by Fubini, this implies that mu tensor nu, well, by Fubini or by definition of the tensor product, which automatically has Fubini, right? It was defined to satisfy the Fubini property. So we conclude that the symmetric difference of the measure of the difference of E minus E1 is smaller than epsilon, right? And this is exactly what we wanted. to show. So we have found a rectangular set inside E, which has almost full measure, almost the same measure as E. And to get the set E2 containing, right? So if we want to get E2, this is exactly the same argument, but with the complement of E instead of E. And I wrote R again here. Excuse me, this should be E, of course. Right. So yeah. So this shows how to find the set approximating E from below. And if you want to approximate E from above, it's the same argument applied to the complement of E, to not E. So this is the proof, assuming that the whole theory is an AP. Yeah, it's a bit more complicated if we don't assume it. All right, I managed to fit it in a slide. Very, very happy. Are there any questions about the argument? Like, is it okay?
The complement of E is also distal.
Ah, that's a good question. Yes, it is, right. If you look, for example, at this definition, the distal cell decomposition, right? You have a formula which decides the phi type. So it also decides the type for not phi as well, right? Because it tells you all the instances of phi or not phi. Mm-hmm. Yeah, no, it's a good point. It's yeah. So in the way I define distal formulas, it is indeed closed under negation and under Boolean combinations, arbitrary Boolean combinations, in fact.
I have a question, not about the proof, but in the definition of distal formulas, is this also closed under like reversing the variables?
So this is not clear, and actually I don't know. I think the way I define it here, I'm not so sure. I think it might be true if the whole theory is an AP. I need to think for a second. But like if I without the global NAP assumption, I don't know. It would be actually interesting to understand. I think if the whole theory is an IP on top of it, that's probably true. That it's closed under exchanging the roles of the variables.
So you gave some examples of distal theories.
Yeah.
But obviously you define kind of like distality also locally, and this theorem holds locally for a formula. So is there any like interesting example we might want to think about, which is a non-distal theory, or maybe not an IP theory, but has a distal formula, and it gives us something that we want to.
Yeah, this is a good question. Yes, it's an interesting question. Let me remind that distality is not closed under reducts, right? It's not closed under reducts because, for example, I might have a formula which is distal in some theory. So, like given phi, I have psi, but I might take a reduct in which I don't have psi anymore, but I still have phi. So, for example, just take like a formula x equals y. Well, actually, take the formula x is not equal to y. If you think about it, if you view it as a formula in the theory of linear order in DLO, let's say, it is distal, right? But it's not distal if you forget the order. So in the theory of equality, it's not going to be distal anymore. Because, right, because in linear order, like if I have a large finite set, and let's say I take a point, which is not in this finite set. With linear order, it's easy to express it. I can just say it's bigger than let's say it's bigger than the biggest point in my linear order. It's just one instance of the formula less than. But with equality, there is no way to say it, right? Because you have to say, I'm not equal to this, I'm not equal to this, I'm not equal to this. And if the set grows, it's an arbitrary large finite set, you need bigger and bigger formulas to say, I'm not in this finite set. So this shows, this shows that, I guess, equality, the theory of equality is not distal, so it's not closed under reducts. Now, it's a very interesting question to know which theories have distal expansions, which stable theories have distal expansions. And yeah, I could say some things about this, but I maybe not now, because I think it takes us apart from it a bit. But it's a very good question that you asked. Yeah, I think there are a lot of like, it's not so clear what's going on there. Okay. Yeah, I mean, sorry, we can either talk more after or yeah, I'll be happy to discuss it more. Okay. Yeah. All right, so we have this. Okay, so this is distality, right? And measures. So I kind of gave you, like, I guess, 3 regularity lemmas, one for general and IP, one for stable, and one for distal, right? And what we didn't do is that these actually characteristic properties. So, like, for example, we saw that under stability, you don't have bad pairs in a regular decomposition. But it's also true conversely that if you have a graph which admits, for any measure, admits a decomposition without bad pairs, then it has to be stable. And vice versa. Like, so for each of these properties, actually characteristic. Yeah. So the picture is quite well understood, I guess, by now for the case of graphs. For hypergraphs, things become much more complicated. And I think Julia gave a talk about this, I guess, about the higher order stability. There's some work on higher order and IP. Well, yeah. So for hypergraphs, there are a lot of interesting questions that remain open, both actually on model theory side, like what are the hierarchy counterparts of all the things like stability and IP, etc. Because, like I said, all of these are properties where we want to say that we have something binary and it's approximated by something unary, right? But then we can also consider something of hierarchy, for example, 3, and wonder when it is well approximated by only binary relations, by things that only talk about 2 variables at a time out of 3, etc. And so things became much more complicated somehow, and yeah, and many questions remain there as well. So yeah, if these things get you curious, I'll be happy to provide more references for where to look about at the hierarchy versions, etc. But okay, so so we have this. So then this is measures. Yeah. So far we have talked about only about measures. Now I want to talk a little bit about the dimension, so the finite dimension that I have alluded to initially. So what is when we talk about the finite dimension, what do we mean? So first of all, it's a whole family of dimensions. So let's go back to the same context that we started with. So we have a sequence of finite sets AI inside MI, some models, yeah, models of some theory. Then we form the ultra product. Okay. And now we want to look at an arbitrary, so given any pseudofinite set, let's say B, a subset of M. So M is I recall M is the ultra product of the MI, right? So given any pseudofinite set, so B, which is itself an ultra product of finite sets in M, we want to compare the size of B to the size of A. Well, size here, I mean like the non-standard size, right? Non-standard size of B to A. Okay. Now, general definition of pseudofinite dimension by Khrushchevsky is to take an arbitrary, so take C to be any convex subgroup of the non-standard reals. Yeah, so R to the power U, the same ultrafilter here. And then we define the associated pseudofinite dimension delta C of the set B simply by taking the logarithm, the non-standard logarithm of the non-standard cardinality of B and modding out by this convex subgroup C. Okay, so remember the idea, I think I've mentioned it in the beginning. What we're trying to do is we're trying to extract the exponent. So like, for example, intuitively, if AI grow like, let's say, n to the alpha, what we want is this power alpha. And yeah, if you just take the logarithm, that's what gives you the power, right? Okay, so this is a very simple definition. You just have to take the logarithm of the cardinality. Yeah, very easy. Okay, but for an arbitrary C, maybe it's not as meaningful. So the one which seems to be the most the choice of C, which seems to be the most useful for various combinatorial applications, is the biggest possible C. So there are two canonical choices which we can make for C. So if we take C to be simply the convex hull, so if I take C the convex hull of the integers, then the associated delta C is called the pseudofinite dimension. Pseudofinite dimension. And we can also do the opposite. So we can try to take the maximal one when we are comparing to the size of a fixed set. So for example, if we take, so this is one possible choice. Yeah. Another possible choice is to take alpha to be the size of some logarithm of the size of some set A. Like we start with some set A given to the finite set, and we normalize with respect to it. So we can take the logarithm of this cardinality of A, and then we take C to be the maximal convex subgroup. So this alpha is going to be a non-standard real, right? Belongs to R to the U. So we can take maximal convex subgroup. Oh, and here I mean with plus, of course, right? To be clear, plus and less than. Maximal convex subgroup of, well, which does not contain alpha. So not containing alpha. Okay. And with this choice, this is what is called a coarse pseudofinite dimension. So we have these two choices, the maximal and the minimal choices of a corresponding subgroup. In the first case is useful when you are trying to compare scales of many different sets involved in the picture. The second case is useful when we are trying to, when we have some given pseudofinite set, and we are trying to compare the sizes of other sets, other pseudofinite sets, only to this one, to this particular one. Okay, now note that in both cases, this dimension a priori is valued in non-standard reals. However, in the second case, we may actually assume that it is real valued. Yeah, so note that this coarse dimension takes values in principle, it takes values in RU. Okay, but up to a canonical isomorphism, we can assume, because we have to look at the quotient, right? We have to look at the quotient by C, like this here. So we can assume that it is real valued. Real valued. Okay. And moreover, we can define it equivalently. Excuse me. So we can define equivalently by taking the standard part of the logarithm of the size of, so this is delta of B, yeah, which we can take standard part of the logarithm of B normalized by the log of A. Okay. So what this tells us is somehow how the power of the growth of the finite sets whose ultra product is B compares to the power of the sets AI, right, which whose ultra product is A. Okay. So this is coarse dimension. Yeah. Sometimes we write delta coarse. I might forget it. So from now on, in fact, we will only talk about coarse dimension. So you don't have to worry too much about this definition with these convex subgroups. I just wanted to mention the more general construction, but we can just take this as our definition really for the rest of the conversation. So yeah, so we take this. So we take the power. We take the logarithm of the non-standard size normalized by the size of a fixed set. Yeah. So like this is this alpha. We have to fix this normalization parameter alpha. In practice, usually, for example, if we talk about graphs, if we're interested to count the number of edges in a graph, it's natural to take alpha to be just the set of vertices, and then, for example, yeah, we compare the size of the number of edges to the number of vertices and things like this. All right, so we have this definition. I hope it's okay. So I can also mention this. Okay, if you're not comfortable with the standard part, let me say it very explicitly. What it means, maybe to spend some time and to develop a bit more intuition. So equivalently, we have, so i.e., we have that delta of B, so the dimension of our set B, like this here, yeah, is the unique number So the unique number, let's say L, in the interval 0, 1, yeah, such that for any epsilon real bigger than 0, actual real, not a standard real. If we look at the set of all I in our indexing sequence, yeah, so that the cardinality of BI is between L minus epsilon and L plus epsilon is in the ultrafilter. Yeah. So where recall that B is equal to the product of the BIs. All right, so we're just picking, yeah. So this is just the parameter, ultra limit or the standard part, whichever language you are more comfortable with, satisfying this condition, right?
Excuse me.
And oh, excuse me, yes, this is not the cardinality of BI. What I mean is the normalized logarithm. Sorry, yeah. So this should be same. Maybe that's what you were going to say, yeah. So this should be the log of the cardinality of BI divided by the log of the cardinality of AI. Is that okay? Or was there some other question also? Okay, okay, good. So we have this definition. Let me just mention a few properties, which I think it makes a good exercise actually to verify. So I hope to include it in the suggested exercises. So why are we even calling it a dimension, right? Like why? Okay. So the point is that it has some properties which are similar to, let's say, Zariski dimension or to Morley rank, etc., that you probably have seen in your favorite context. So assume we have so A, B. Assume these are all pseudofinite sets. Okay. Then we have the following properties of the dimension. So the dimension of A. So A, remember, A is special, yeah? A is our normalizing set, and then I'm allowed to have some other pseudofinite sets. So the dimension of A is 1. Well, we would like to, right? Because we're normalizing with respect to A. Now, the following is important point, that the dimension of a union of two sets, let's say B1 union B2, is the maximum, simply the maximum of the dimensions of the two. So delta B1, delta B2. So we have this for any pseudofinite sets B1, B2. Okay. So this is the same property you have for Morley rank, for example. And here you have it for dimension, and this of course because the properties of the logarithm, yeah, the basic properties of the logarithm. And also importantly, we have a property which is a bit like Fubini. We have this fiber-wise condition. So assume that I have, let's say, so it's you can call it subadditivity equivalently. Yeah. So assume we have, let's say, a set Y contained in, let's say, a times a to the m. Okay, and assume we have Z contained in, let's say, A. So assume these are pseudofinite. Okay, and assume that the dimension of Z, let's say, is alpha. Okay, and for all pairwise distinct elements, let's say A1 through AM in Z, we have a bound. So assume for each fiber we have a bound on the dimension of the corresponding fiber. So let's say we have delta for X in A. We have that if I look at all X which are connected to A1 through AM, yeah, let's say this has dimension less or equal than beta. So I have this, you should think about it like we have a binary relation, so that each fiber has dimension bounded by beta. Then this gives us a bound on the dimension of the set of all X and A. Okay. So that there exists Z1 through Zn in Z, such that we have they all distinct, not equal to Zj, I not equal to J, and set like this, what we get is that it is bounded by M alpha plus beta. So we have this kind of counting by fiber, or like double counting type of arguments, which apply to this, and there are more properties. So I think I'll try to list a bunch of properties and the various assumptions that are useful of this dimension, and yeah, give it as an exercise in the exercise section. But okay, so we have this coarse pseudofinite dimension. So I'm not saying coarse every time, yeah. Now, when is it interesting? It's interesting when it's possible to prove some comparison between this dimension and some other associated dimension that you already have in your theory. So, for example, if you're stable, you can try to compare it to the rank, or in omega stable, you can compare it to Morley rank. And in various nice contexts, there are some results which apply to it. So let me just mention one application. There's an open conjecture in graph theory called the Erdős-Hajnal conjecture. So let us say definition. So let me just mention this quick application. So definition, yeah, given a family of graphs, let's say H of graphs, or let me call it not H, let me call it F. We say that it has the Erdős-Hajnal property. Or simply the EH property. If there exists some alpha, positive real number, yeah, so that every graph in F, every G in F, it has either a clique or an anti-clique. Either a clique or an anti-clique. Yeah, so this of size, at least. So if G was, let's say, had the set of vertices V and E the edges, so it has a clique of a complete set of size at least V to the alpha. Okay. you might have heard that normally, just using Ramsey theorem, we can always find a subset, a clique or an anti-clique, right? But Ramsey theorem has exponential loss of size. So it's always possible to find a clique or an anti-clique of size given by the logarithm of the number of the vertices. So this is asking, is it possible? Well, this property tells you that you can do much better. So you can find a complete set of with only polynomial loss in the size. Okay. And this is easy to rephrase using the coarse pseudofinite dimension, right? So i.e. in the ultra product, we have a clique or an anti-clique of positive dimension. So we have a complete set with delta, well, let's say complete set S contained in V with delta S greater than 0, right? Or greater or equal than alpha, if we are fixing alpha. Yeah. So the question, the Erdős-Hajnal property, what it really saying is that if in an ultra product of my family, we can find a complete set of positive dimension. All right. And one application is that, so for example, every stable graph, every stable family of graphs, so every family of graphs with a stable H relation, so stable in the ultra product, yeah. So I'm saying in the family we have somehow uniform bound on stability, but with a stable edge relation satisfies it. Okay, and this was implicitly proved even by Erdős and some others. Then, like explicit connection with stability was realized by Maliaris and Shelach, and yeah, there's a very nice, very simple proof using pseudofinite dimension of this result. What we really use here is that this pseudofinite dimension drops when you fork in a stable theory. Like when the rank drops, when Shelach's 2 rank drops, the pseudofinite dimension also drops. Okay, and this is completely open for an IP if this result holds or not. But I have to stop here. I'll say some more things maybe next time about it. Okay, but yeah, thank you very much. I'll stop.
Okay, any questions?
Quick question. So in this ultra product here is just over the family that you're looking at, right?
Yes. So here the dimension is normal. So what I called A before, in this case, I guess it's going to be just the so AI here is just the set of vertices V of the graphs in this family. Maybe let's just write it like let's say GI for I in omega. Yeah, it doesn't have to be countable, etc. But just to be consistent with my previous notation, let's say we have a countable family of graphs, GI, and then what I called AI before is now the set of vertices of the corresponding graph. So let's say we write GI as VI EI, so the vertices and the edges, and then the ultra product with respect to the VIs and this coarse dimension that I wrote here. We are normalizing it with respect to the VIs again. Yeah.
Any other questions? Oh yes.
Yeah. What is a clique or an anti-clique?
Sorry. No. I should have defined it. Yes. So this simply means so a clique is a set of vertices, so that you have edge between any 2 of them which are distinct. Yeah. So in that sense, it's like a complete set. You have an edge between any 2 vertices in a clique. So a set like this is called clique. And anti-clique means a set so that there are no edges at all on it. So between any 2 vertices in an anti-clique, there's no edge. Between any 2 vertices, there's no edge.
Thank you.
Yeah, it's a graph theoretic terminology, I guess. Sometimes it's called a homogeneous subset also in other literature.
Isa?
Maybe Artem, could you use a word where distal theories allocated in the universe?
Sorry, can you say it again?
Distal theories, can you lose a word about where they are, in our universe with the dividing lines?
Let's see. So all of this is inside an IP. So I can draw it, I guess, like this. So we have, what do we have? Okay, so this is stable. There are too many universes these days, So this is stable, this is simple, this is an IP. And I guess I should draw distal like here. Actually, yeah, let me remove this an IP from here. So this whole thing is an IP. And then I can put distal here. So we have the two extreme opposites somehow inside an IP. So we have stable and we have distal. And there's stuff in between, which the hope is that in some sense, the stuff in between in an IP is a combination of stable and distal. There's some results which go in this direction, but like this combination can be quite complicated. So yeah, but the idea that these are two extreme opposite behaviors inside an IP. But by what we already discussed a little bit, there is also some combination of the two that can happen, namely when you have a stable theory, which has a distal expansion. And this will be exactly the context actually that we will need in the next lecture. Somehow it seems to be the best of all worlds when you have a stable theory which has a distal expansion, because then you simultaneously have the rank, like forking calculus that stability theory gives you. And also you have this cell decompositions that can be used to obtain various combinatorial consequences. And let me just mention a couple of examples of stable theories, if that's okay. Yeah, stable theories with distal expansions. And this is basically almost all of them. I think like all the natural ones you can take tend to have a distal expansion. So let's say, what do we have there? We have ACF0, DCF0. What else do we have? What other stable theories are there?
Fussy constructions in there.
Yes, right. Yeah, okay, yeah, that's an interesting case also. So for uncollapsed Khrushchevsky certain uncollapsed Khrushchevsky constructions, but I was saying natural stable theories. Yeah, I know it's not for most people. It's not the most natural. Uncollapsed. Sure, yeah. So uncollapsed Khrushchevsky constructions, etc. It is actually open, and I think it's probably a difficult problem whether the free groups have distal expansion. So by deep result of Sela, free groups are stable. I mean, all abelian groups, I should mention also, abelian groups. So, but by deep theorem of Sela, we know that non-commutative free groups are stable, right? But it's open if they have a distal expansion or not, and probably it's hard. Maybe let me mention also a couple of non-examples. So non-examples. This would be ACFP. Yeah, so positive characteristic fields don't have distal expansions. It's a curious fact, right? Because for a while this was the only theory for which we knew there is no distal expansion, the only stable theory. Because and what else we have? We have expander graphs. If you're into that kind of combinatorics, it's a very important kind of graphs. But let me not go into that too much. Like if someone is curious, I can say more. And very recently, we have Banach spaces in continuous logic. So this is some examples and non-examples, okay? And like I said, all of this is, so Distality lives inside an IP, yeah? So this is good enough, this map and examples.
What about collapsed Chomsky constructions, as you emphasize in collapse?
Yeah, so that's open. What we know is that they are locally distal, in the sense that every formula that I gave, right? Like, I guess what we know is that for if I take any formula in a collapsed Khrushchevsky construction, I can find some psi in some expansion, which gives a distal cell decomposition for it. Yeah, but we don't know if there's one expansion which contains all of them. Like, so we don't know if there is an actual distal expansion, but somehow it's locally distal. So most combinatorial consequences do survive. I mean, all combinatorial consequences that we know of, they hold. But yeah, but it's not clear if there's an actual distal expansion in the collapse. And again, I'll be happy to talk more about this. Yeah, I think. Yeah.
Thanks.
Oh,
I think I sent you an email about this actually, but I
oh yeah. Oh yeah. Yes. Sorry.
No worries.
So you are. Yeah. I'm going to respond soon. Yeah. I'm sorry. I just been busy.
No. I just want to make sure that we're getting everything, and I was wondering. Sorry.
No worries.
Okay. So I think we probably don't have more time because we. So what time do you think of meeting for?
6:15.
Pardon?
6:15.
6:15.
6:15.
Okay.
We leave, right? Not
Yes. Well,
be there at 6:15.
then let's thank Artem again for this talk.
Thank you.